Okay, so I I suppose I'll get started, and people are welcome to join in midway. So I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis. Today we will be discussing the contents for the final week, that is week 12, which has to do with strain gauges. Yeah, good evening. Mr. Rajaman, are you able to hear me? Fine. Okay, okay. Okay, so let us move on to the first question of the day. Answer true or false for the following statements in one specific order. Type to T for true and F for false without any spaces. So we have to report it without any spaces is what. That is a reporting issue, but we will first focus at the question. So the question says A. Flux is required in soldering operation to remove and inhibit oxidation. Ordinary cellophane tapes available in the market can be used for masking for the strain gauges. Tinning of wire helps to ensure surface wetting and good heat transfer during soldering. And spikes formed during soldering are beneficial for the beneficial during strain measurement. So we just need to answer it in the order. So flux is required for soldering to remove and inhibit oxidation. This is very true. Because even if we see it is related to the fourth point actually. If we see that lot of spiking is happening, that means implies that there are some impurities at the tip of the soldering iron which needs to be removed. This also plays a part in tinning. So first in tinning, what we do is first we will take the wire, wind it into a strip, into a this thing. Same goes for the soldering iron tip also. We will apply it with some flux and then tin it using the solder material so that it has a coating over it so that soldering becomes easier. So flux is definitely useful in that operation and very essential in fact. There are many solders nowadays that come with a flux core inside, which are quite useful. So as soon as we put this onto the soldering iron, the flux inside will also melt, which provides for a better soldering experience. Ordinary cellophane tapes available in the market can be used for masking. What is masking essentially? Masking is protecting the strain gauge when we solder it. Essentially, we know that our strain gauge will have terminals like that. Let me just draw it roughly. So when we have to solder our wires to these terminals, essentially we will be pasting a tape over this so as to mask this out, and so that this doesn't get disturbed by our soldering operation. So that is the entire purpose of masking. And this is very specific because the type of adhesive that the cellophane tape has, that could perhaps also disturb and lead to certain errors in measurement. So it is always advisable that the cellophane tapes that are being provided by the strain gauge manufacturers are to be used for that particular strain gauge. So this is not recommended. Tinning of wires helps to ensure surface wetting and good heat transfer during soldering. Yes, this is very much correct. In fact, tinning is recommended not only for the wire, tinning is recommended for not only for the wire but also for the soldering iron tip. Wire as well as soldering iron tip. So once we ensure that this is done, our soldering becomes easier. Okay. And last point, spikes formed during soldering are beneficial for strain measurement. These can essentially, this is this spikes are an example of bad soldering practices, as shown in the lectures also. Poor soldering. Yeah. Yes. Okay. Image I don't have as of now, but you can. I'll tell you if you have the lecture open. I can tell you where it is. Okay. Spikes in soldering is not clear. No, there will be. See here, there will be extra. If you have a blob here, sometime have you? I'm sure you would have soldered, right? When you try soldering, what will happen is you have the soldering iron tip. Let us say this is the soldering iron tip. It will actually be a little more blunt, like that. And then you have the soldering wire. So when you bring this close to the point where you want to, perhaps the tab to be soldered. So once this is brought together here, and once you remove it, essentially you will see a big blob of sharp this thing coming out. That is what is referred to as a spike. Yes. The precaution being, one is that the tip should be clean. Let me just try to Google it. See this, no? These things occur, these things you're able to see in the screen, the spikes. Yeah, so these things have the propensity to damage the instrumentation also. One reason for this is that the tip is not cleaned, the wire is not tinned properly. The second reason is that lifting operation, essentially lifting this soldering iron and the solder should be happening simultaneously. It should not be that one precedes the other. If you let the solder touch the tab and then lift the soldering iron, there is a possibility that the solder might get stuck to the fused with the tab. On the other end, if you remove the this thing first, solder first, then you won't have proper this thing, proper soldering happening. So this has to be, it's a matter of practice. It has to be done simultaneously, provided that the tip is tinned and cleaned properly. Definitely you can avoid. Yes. And it is not as tough as you think. You just have to do it a couple of times to get the hang of it. Uh, yeah. Even I would consider I don't consider myself to be trained in strain gauge pasting, and I have done soldering without spiking a number of times. Yeah, so that you can rest assured that it is not that hard. Just that one main reason what people try to figure out is it is some technique based thing. One part of it is technique based, but the other is that the possibility why they could not be avoiding this is because the tip is not clean. It needs to be tinned properly first with flux. Only then we can avoid that. So that provides for better wetting. So it is definitely not beneficial. In fact, it is a drawback and an example of poor soldering. So which materials? No, welding is see soldering is you are having a lead wire and you are trying to fuse that a wire with another wire by means of lead solder, which might or might not come with this flux. Welding is essentially fusing any two metals. Yeah. You have transducer application inside for all the wiring circuitry, everything as soldering only. Wherever there is a circuit, there is soldering required. But for our stress analysis perspective, we should ensure that strain gauges are properly soldered. Not only strain gauge is a hard thing to paste. Once it is pasted, needs to be aligned properly, cured properly. Then the soldering needs to be correctly done. Over and above that, we need to ensure that ground resistance and there is no flux leakage and all that, which will come in the questions that we see further. So after ensuring all that only, we should move forward with measure. Okay, so I hope that that is clear. Yeah. Okay, so let us move to the next question. Yes, I have a doubt about numerical question from week 10. Uh, we can take it towards the end of the session, maybe. I hope that that is okay. Yeah, all right. If a T rosette is used to measure the shear strains, how many channels of the strain measuring instrument are required to take this reading? So essentially, T rosette is when you have strain gauges in perpendicular directions. I will try to approach this from an alternate perspective. Let us say that we are having a shaft subjected to pure shear, a shaft subjected to torsion, which is essentially you are having a pure shear condition. Now, if we want to measure what the shear strains are, we know that the same thing we can transform it in another coordinate system, and we know if this is tau, then this happens to be this also happens to be tau, and we will have compression here, which is equal to tau. This comes from our basic stress transformation tau. So if I were to name this direction as 1 and this direction as 2, so strain along 1 is nothing but tau by E minus mu minus tau by E, because the other side is compression. So epsilon 1 is nothing but tau by E into 1 plus mu. So if I align my strain gauge in that direction, the epsilon 2 will be minus tau by E minus mu tau by E. Epsilon 2 will be minus epsilon 1. So what this implies is, if we have a T rosette, we may as well connect it to one quarter bridge of a Wheatstone, quarter bridge connection, and we may as well measure the shear strains that are coming up there. So we require only one channel essentially in case of a T rosette applied to measure shear strains. So I hope that this is clear. Okay, so I take it that that is clear. Let us look at this question. A stress gauge to measure stress in the x direction has two elements oriented at an angle with respect to the x-axis as shown in the figure, which decides the functionality. So this direction, basically this orientation, this is kept if this is to be named theta A and this is to be named theta B. So theta A is purposely kept equal to minus theta B. From the equations, you can see it from the lecture. So the angle of orientation theta in this case should be which of the following relation, where Poisson's ratio is of the base material is given by mu. So essentially stress gauge, what it works on the principle that this is a common conductor. This is connected here. It's a single wire. So essentially first we will calculate strain in this direction and strain in this direction. Then using our strain transformation law, by taking this as the basis, we'll take sigma 1. This is sigma 2 direction. So with basis meaning unit vectors. along 1 2 direction, we'll write the expression for epsilon A, epsilon B. And we know that along 1 2 directions, gamma xy is 0. Why? Because that is the principal basis. So there is no shear stress or shear strain. Based on this, when we write and invoke invariance, invariance meaning invariance of a tensor. The first invariant of a tensor is the diagonal, sum of the diagonal trace of the stress tensor or strain tensor is invariant. Epsilon xx plus epsilon yy. This will remain a constant, which is also called I1. Similarly, trace of the stress matrix is also an invariant. So upon invoking all this, there is a long derivation that is shown in the lecture, which I don't intend to replicate here. But based on these principles, when we do, it will come out that theta is tan inverse of mu v for this to function as a stress gauge. Tan inverse of root of mu. I'm sorry, I said mu v, I think. What I meant is tan inverse of root of mu, where mu is the Poisson's ratio of base material. Base material meaning the material in which we want to measure it. So I hope that that is clear. So for this derivation, one can refer the lectures. But this is based on these principles. First, we take that basis as the eigenbasis, and then we use stress transformation. And since it is the principal eigenbasis, our shear strains are 0. We invoke invariance and do some algebraic manipulations to get this expression. Okay, so I take it that that is clear. I'll just move it here. This is I1, I1, I1. This is for I1 strain, this is for I1 stress. Okay, so let us look at this question. The stress gauge construction is based on which of the following principles? So, first, let us look at how this construction comes about. We know that delta R by R for any strain gauge is SA axial, meaning SA is sensitivity in the axial direction, axial strain plus KT epsilon T, where KT is our transverse sensitivity. Now, our axial strain, can we write it in terms of stress? It is axial stress minus mu transverse stress by E. Similarly, my transverse strain will be transverse by E minus mu axial by E. So these two I can write. Now if I were to substitute that back, I'll get delta R by R is SA into sigma A by E minus mu sigma T by E plus KT sigma T by E minus mu KT sigma A by E. Let me just add one page here. So if I were to separate this out, Okay, let me just, I take this and I take this together. This is 1 plus SA into, I'll get this thing first, this thing second. Let me delete this and take this here. So I've just moved around the brackets, not done anything major. Okay, so delta R by R is given by SA sigma A by E, say, into 1 minus mu KT plus SA sigma T by E into KT minus mu. So if we could reduce this somehow, what this tells us is this expression, if we see, it directly relates our stress to change in resistance when this term is nullified. So how can this be nullified? To nullify, we keep KT is equal to mu. Once we keep KT equal to mu, then delta R by R is SA sigma A by E into, or rather, let me take E inside. It doesn't matter actually, let me leave it that way. 1 minus mu KT. Or if we have to reduce it, 1 minus mu squared essentially. So for this to function as a stress gauge, we need to keep the transfer sensitivity factor. The transfer sensitivity of the gauge should be kept equal to the Poisson's ratio of the base material. So that is how our stress gauges are constructed. So I hope that that is clear. Yeah. Have you noted it down? Can we move on? Yeah. Yes, that is for the, we have one table to correct for our strain measurements. But if we want to use that as a stress gauge, you look at the question. No, it says if that has to be used as a stress gauge, what is the constraint that we need to supply in order for this to function as a stress gauge? Okay. Yeah. Okay. So I take it that that is clear. Let us look at this question. Alice asks her friend to bond a strain gauge for conducting experiments at a as a part of her project work. Okay. After the prescribed curing time, Alice checks the installation to complete curing of adhesives. Whether the bonding has taken place properly or not, that is what we are trying to see. Select the methods that are possible for this. So, one is apply a small strain to the specimen bonded with a strain gauge and check the zero shift. What is zero shift? When we apply and when we engage a load and then disengage it, it should ideally return to the same strain value. If there is an offset, that implies that there is a zero shift. Now our if a strain gauge is bonded properly, then studies show that even cycles of 1000 microstrain, if you apply, then zero shift is less than 2 microstrain. This is provided the bonding is proper. That is, the adhesive has cured. So this is one of the check. So we apply a small strain to the specimen with the strain gauge and check for the zero shift. Yes, this can be done. If it is not possible for us to apply a mechanical strain, we can also go for temperature cycle, so that and check whether the zero shift has come back. If it has not come back, then in case zero shift is not within the prescribed bounds, it implies that we need to wait a little longer. We rushed it, so we need the curing to take place properly. Bonding improper. Okay. Now the other options say that we can tap the specimen with a finger and observe the effect on the strain indicator. This is strictly to be avoided. Any handling, rough handling of strain gauge can irreparably damage it. So this is not prescribed. And the last one, apply a uniform pressure over the strain gauge using a piece of rubber, and observe the effect on the strain indicator. This is a check, but this is not a check for curing. Essentially, this method to apply a rubber pressure over the strain gauge is used to check for voids or bubbles. Why? Because if the bonding, let us say that there is a void that got left out, so the conductor there, the wire, the strain gauge wire there is unsupported. So when we apply the pressure, it will have some change in length, which will get reflected as the strain. Whereas if the surface is properly prepared and there are no voids or bubbles, and if the bonding is proper, then we wouldn't see any change. But regardless of that, we should not use our hands to do it. That is why we are using rubber, so as to not to damage it and to apply the pressure uniformly over the strain gauge. So that is what this check is for. This is essentially to check for voids or bubbles underneath, but this is not for checking our curing of the adhesive. So I hope that that is clear. That point is clear. This is a check, but not for this one. Yeah, tap the specimen with a finger and observe. So in the process of doing that, because we know that the strain gauge foil, it's a metal foil. It is so thin that we handle it using tweezers, not even with hands. So it is very important that we don't indulge in these practices, so as to keep our strain gauge safe, because these are expensive. Yes. And fourth option is wrong in this context. This is definitely a method, but not to check the curing of adhesives, but to check the presence of voids. What? Pictorially. You have the specimen like that. You have a strain gauge here. You take a piece of rubber and then you press it over that rubber and press this so that it gets uniformly pressurized, and then see if there is any change in the reading. Yeah. Where should I put it? Okay, let it be here. Okay. So I hope that that is clear. Let us look at the next question. So this says, based on experimental observations, the deviation of strain gauge value from actual value due to hydrostatic pressure effects on strain gauge installation in the case of high pressure applications is given by dp kt into the pressure. This is the applied pressure. We have our this thing, compressibility constant, which is essentially E by 1 minus 2 mu. That is what it will come out to be. It is not exactly bulk modulus, because bulk modulus will have a 3 here. Okay, and this is one coefficient. So the question asks, what is this factor dp, the coefficient factor dp, dependent on? So essentially, when we have hydrostatic pressure, meaning that in the plane you have strains in two direction. What is hydrostatic pressure? You have a stress cube, stress element somewhere where everything is either tension or compression of equal magnitude. Let me just say that. So in such cases, our strain values, it is noted that in such applications, when we have, for example, if we have a spherical this thing with an equal amount of pressure that is applied, in such cases, up to a strain value, the value of the strain is independent of this pressure applied. Whereas if we exceed that pressure, then it will start showing deviation from our actual value. So this extensive studies have taken place towards this in order to quantify this. And what is noted in the experiment is this factor that needs to be subtracted from for example, from the strain gauge, we will be reading our E hat, which is apparent strain. This is the value that our strain gauge meter will show. And this is the correction for the pressure, which is given by the dp, whatever we saw here, into pressure P. So our true strain in this case would be our apparent strain minus this correction. Up to a certain pressure, this difference will not be large. Beyond a certain pressure, this will begin to pick up and we will see significant deviations, which have been extensively studied using experiments. So the question it asks is, what is this dP dependent on? So even, yeah, yes, yeah, this is dependent on curvature and the gauge material, exactly. So these three, it depends on these three, and this has been reported experimentally by there was some scientist name, I think Milligan or something. You can just refer the lectures regarding this. But extensive studies have been done, and this is the dependence that has been found. So compressibility constant and no, 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 no. Okay, let me just clarify that. This, rather, I should say this is K capital T, no? So KT is, yes, yes. But it's a good question that you asked. It is important to get this out in the clear. In fact, it never occurred to me that people could see it this way, but it's very important that you ask this. This is, yes, yes, exactly. So it's very relevant that you ask this. Let me just put it in a box, color it and all, so that people remember it. That not the same. Okay. Okay. So here we are talking in case of hydrostatic pressure cases, the compressibility constant. Essentially, we could have left it in terms of E and mu only, but to make it more compact, they have done some rebranding. That's all. But yes, this is an important question that should be kept in mind. Okay. Pressure applied. Okay. So I hope that that is clear. So let us look at the next subsequent question. The effects of moisture on strain gauge installation include which of the following? So moisture, it is not necessary that our strain gauge and specimen needs to be dipped inside a fluid for it to have moisture ingress. Moisture ingress may as well happen from the surrounding environment. And what are the effects that it has? First is you have, let me take that same, this thing that I drew here of the, similar to what flux leakage does. If there is leakage between these two, if there is leakage between the specimen and the strain gauge, flux leakage in because of flux, what will happen is when you there is a testing apparatus from Vishay, it is called 1300 P1300 indicator. So when we plug our strain gauge to this, and this is to check the resistance, check the gauge resistance. So one thing is it will check the gauge resistance as such For example, we saw in the earlier sessions also, we can use a strain gauge of 120 ohms or 350 ohms. So first thing is it will tell you the deviation of that. That is one part of it. When we attach the specimen and the strain gauge connected to P1300, it will tell me the ground resistance. Ground resistance meaning if there is any leakage between the strain gauge and the specimen. If there is leakage, I say ideally that resistance should be as high as possible. In laboratory setting, it is said it will be on the order of 10 mega ohms, 10 power 6 ohms or so. But due to some reason, if there is a compromise there, then there will be an ingress. That compromise could be due to moisture ingress or due to flux leakage. In case of flux leakage, we can easily use uh, the cleaning liquid that they give and clean it out. But in case of moisture ingress, we can't do much about it. But it definitely leads to reduction of the gauge to ground resistance. So if one is true, second is it cannot be true. Reduction in the effectiveness of the adhesive in transmitting of the strains. Yes, adhesive also can get affected due to this. And the entire theory of strain gauge hinges on the fact that strains are faithfully transferred. Mr. Rajamana, could you kindly mute because there is some sound that is coming. Yeah. So essentially, our effectiveness of the adhesive. Yeah. So the entire strain gauge theory is hinges on the fact that strain in the specimen is faithfully transferred to strain in the metal foil. This metal foil that is turned into the strain gauge. So if that adhesive is compromised, then definitely its effectiveness to deliver the strains, and therefore our strain gauge installation itself is questionable, and this is one of the factors that gets affected due to our moisture ingress. And significant increase in the strength and rigidity of the bond. Essentially, this will reduce. It leads to reduction, not increase. Reduction in the strength and rigidity of the bond, and significant increase in the resistance due to eroding of the gauge filaments. So essentially, what will happen is as the moisture sets in, this will lead to electrolysis, which will precipitate our increase in gauge resistance. And we saw that our change in the resistance, it has factor some constant into change in resistance by resistance. There were several this classic equation of the Wheatstone bridge, if we see. So this affects that. Once our resistance increases, because the other resistors in the Wheatstone bridge are simply shunt resistors, which are of fixed value. Whereas if moisture ingress leads to an increase in one of the resistors, meaning the strain gauge, what will happen is its sensitivity will not be at its peak, because we saw for sensitivity of a strain gauge instrumentation to be at its peak, the ratio of all the resistors needs to be maintained at unity, meaning all the resistors should preferably be at the same resistance initially. So this leads to problem like this. So this needs to be kept in mind. So I hope. Sorry. Yeah. Yeah, we protect. See, even photoelastic models, we keep it in the desiccator to curb this. Essentially, you cannot foolproof anything 100%. We try it. And another fact of the matter is that this is something we are trying to study, right? So once we know what all problems that moisture can cause, then with latest technologies, we'll come up with sealants that can better protect this over a given period of time. temperature, humidity both play a major role in this. Exactly. Yes. So if we have to monitor bridges which are, bridges run over water bodies. So in such cases, if we are analyzing a sea link, then we have corrosive atmosphere. So all these things would definitely play a role. So once we study what are the effects of these on the strain gauge instrumentation, we can take appropriate remedial measures or prophylactic measures so that these problems don't affect our long-term readings. Because installation, as we saw, it is quite challenging. But once it is done, it is reliable. Yes. Yeah. Yeah. Yes. Yes, depends upon the length of the bridge, depends upon which is the point we are trying to study, depends upon which is the span we are trying to study. For example, if we have a simply supported bridge, let us say, which is supported over a pillar, which will be essentially kept on bearings. So this will have some bearings and this will deliver the load to the bottom. Now, where do we anticipate if this is if let us say that my bridge goes like that, where do we anticipate the maximum stress to be? Essentially, this is subjected to vertically downward loads. So our bending moment maximum in an ideal condition occurs at that point. That is provided it is simply supported. So yes, yes, yeah. So essentially, we will be identifying key points where we need to place our strain gauges. So is bending the only problem in case of a bridge girder? No, shear also can affect. So shear, we know near the supports there is high shear. In such cases, we will be let us say that this is a plate girder. Let us say that this is a plate. In such cases, we know from our basic theory of strength of material that our shear stress variation is parabolic. So what that implies, at the neutral axis of this section, my shear stress is maximum and there is no normal stress. Now I can justify one way that bending stresses are almost 20 times that of shear stresses and I needn't bother about shear and go on scooping the material out. What will happen if I make the plate very thin? As we saw, in case of pure shear, at the neutral axis, I have the maximum shear stress, which is tau max. So in such case, what this will do is I have a stress element like that. I simply this can be represented as tau max like this and tau max as compression, right? By simple transformation. So let us say that I went on economizing this and make the plate girder very thin. So what is this? This is compressive stress. So in case of a very thin plate girder, compressive stress can lead to buckling, local flange buckling. So these are very big problems. In case there is web buckling or this is web buckling essentially, but in plane of the flange, buckling can take place. So buckling is a structural stability problem. In such cases, the entire bridge usage is put under risk. So we will identify such key points and then place strain gauges over there so as to see that due to movement of the vehicles and whatnot, if the structure is very old, that our strains are within the permissible limits. Is it clear, sir? Yeah. Earthen dams are no, but essentially these are bulk structures. So where is the strain or stress you want to measure? See, in case of optimized structures, because a dam is a bulk structure, right? So if you see a dam, essentially it is a triangle. a somewhat glorified triangle. So as you go down, the base also becomes wider from stability perspectives because essentially this has to hold on to water here. So this is water. So I'll have a distribution like this. So essentially the water will try to topple it, whereas its self weight is the only restoring moment about this heel. So gravity structures, essentially stress concentration would be only near the toe, and that there we can provide local reinforcements and take care of that issue. Yeah, essentially here what they will do is they will extend the foot here. They will provide an additional cut-off wall and all that so as to design this. So where strain gauge and to the very scale of the structure, what value can you get reliably is also questionable. Whereas if we go to a bridge structure where we are optimizing, why we went from a box section to an I section, because we found out that for bending members, the farther we put the area, farther we put the material away from its neutral axis, the better it behaves. I is also dependent on the distribution of the area. It is a second moment of area, right? So distribution of the area also becomes important. In such cases where we have optimized, we want to make sure whether it will hold or not. Or old structures which have been optimized. Here also in old dams also there would be retrofitting and safety checks taking place, but I doubt if that will be done with strain gauges. Essentially, that will involve cover protection and things like that. Okay, yeah, all right. So let us look at the next question. A chemical has to be transferred through a pipeline into a gas tanker for transportation. Taking account taking into account the pressure of the gas, let us call that P. Pressure of the gas to be filled in the tanker, the inspection team suggested a stress analysis using a strain gauge. Okay. Why? Because this is a pressure vessel. So we need to ensure that pressures are not, because explosive decompression can be very catastrophic. Okay. They pasted a strain gauge along the circumferential direction. So essentially we have our pressure vessel, so to speak. Okay, so which is the circumferential direction here? It is this. In the cross section, if we see, here we would have pasted, so this is the circumferential direction. Longitudinal is into the plane, longitudinal is this way. Okay, so here it is internally applied with some pressure. And we have taken the magnitude of that pressure to be P to start with. They pasted the strain gauge along the circumferential direction. The strain gauge material is different from the pipe material. And the Poisson's ratio of the pipe material is 0.29. This is of the pipe, 0.29. The gauge factor of the strain gauge is given to be 2. And the transverse sensitivity of the gauge is given to be 1.1%. So this is 1.1%. Mind you, this is small t, as you had also remarked earlier. You please keep note of that. Okay. The Poisson's ratio of the calibration beam material is taken to be 0.285, which is generally what is taken. That is how transverse sensitivity is reported by the manufacturer. They will conduct experiments that similar to cantilever experiments. They will be conducting and preparing a chart, and they will be giving that. So if we use that strain gauge in a base material which is other than this, then it would precipitate some errors. Okay, so let us look at this question. The ratio of the longitudinal strain to hoop strain in the pressure vessel is what? Is what is asked. Now let me just add a page here. So longitudinal strain. Let this be epsilon L, and then hoop strain. Hoop or circumferential, it implies the same thing. Hoop or is epsilon H, let me call it. Now in case of a pressure vessel, I know that longitudinal stress, longitudinal, we have closed pressure vessel, we have longitudinal stress and sigma H. The derivations are very straightforward. This will come to PR by T, and my longitudinal will come to PR by 2T, where P is my pressure applied, R is radius of the vessel, T is wall thickness. So for thin pressure vessels, this holds good. Okay, so based on this, can I write an expression for epsilon L? It is sigma L by E minus mu pipe sigma H by P. What does this come to? PR by TE minus mu pipe PR by 2TE, which is PR by TE into 1 minus mu P by 2. This is epsilon L. Okay, so far so good. Similarly, epsilon H can be written as sigma H by E minus mu sigma L by E, which is PR by 2T E minus mu PR by T E. If I take it again, T E, it is 1 by 2 minus mu, which is 1 minus 2 mu by 2. Okay, so yes, in the exam you're asking? No, this is coming from basic strength of material, right? No, no, those most probably will be provided. Okay. What comes from basic strength of material, that students will be expected to know. But other than that, I think they will be providing a data sheet. Data sheet meaning some of the significant formulae or things like that. They generally provide that. Okay, yeah. But I would recommend that you also get this clarified from the forum once. Okay, you just post it in the forum, in the discussion forum, you post this so that because essentially I am serving as the additional TA for this course. The actual regular TAs for this course are different, but I am given to understand that they do provide data sheet, but I would recommend that you get it confirmed once anyway, because the main focus is on trying to see how much you have understood, not your memory. Where anybody can floor anyone with such complex formulae. The idea is only application, not memory based. I hope that that is clear. Okay, So we have got our epsilon hoop as this. Okay, let me forget that. Yeah, all right. I'll just color it like that. Now, in our question, we have been asked the ratio of the longitudinal strain to the hoop strain of the pressure vessel is what? So, epsilon L by epsilon H is what we have been asked, which comes to 2 minus epsilon L is okay. Yeah, see, there is one problem here if we see. Okay, epsilon L longitudinal stress will always be less and hoop stress will always be more. So when I apply longitudinal stress here, 2 should be here and not here. So I hope you got what I'm trying to say. Just got a little misplaced. It's okay. I'll correct it now. Okay, so epsilon L is PR by TE into 1 minus 2 mu P by 2. It just got flipped. And here I will have 2 not here but in the second term. So what will this come to? It will be PR by TE into 2 minus mu by 2. Okay, this is my hoop strain. So if I take the ratio of longitudinal to hoop, it will be PR by TE will cancel out and I'll get 1 minus 2 mu P by 2 minus mu P. This is my ratio of the strains. And I have been given mu P, I have been given that it is 0.29. So let me just substitute it. It will be 1 minus 2 into 0.29 by 2 minus 0.29. This will come to on 2 minus 0.29 comes to 0.245, 246. Okay, so this comes to epsilon L by epsilon H is 0.246. What is the apparent gauge factor? Is what we have been asked. Okay, so let us see how this comes about. So essentially, we have yeah, let me add one more page here. So for any strain gauge, I have delta R by R is given as SG. Essentially, from first principles, if I see, it will be SA epsilon A plus ST epsilon T. Now defining ST by SA to be KT, I will get delta R by R as SA into epsilon A plus KT epsilon T. Okay. Now epsilon T, if I replace by epsilon mu epsilon A, then delta R by R comes to SA into epsilon A minus mu epsilon A KT, which is delta R by R is SA 1 minus mu KT into epsilon A, which is what is conveniently termed as my gauge factor into epsilon A. This is the general theory behind it. Okay. Now, in case epsilon T by epsilon A is not known, this is for a known case. In case it is not known, then I would have to treat it differently, which is essentially delta R by R is SA into epsilon A plus KT epsilon T, which is SA into, let me take that out commonly, into 1 plus KT epsilon T by epsilon A is delta R by R. Okay. This happens in the case where I don't know what the ratio is. Whereas this is in the case where the strain gauge manufacturer does it on a known material and provides that epsilon T is minus epsilon A. In such a case, they will do it. So if I see this term would comprise my gauge factor into epsilon A. This term will imply that this is my gauge factor for a material where epsilon T, where this thing was same, this was kept same. That is the base material over which the strain gauge was tested and the base material over which you are actually applying the strain gauge is same. If that does not happen, then we will have something called apparent strain. This is what we will measure with something called an apparent gauge factor and apparent strain, because mismatch of calibration Poisson's ratio versus base material Poisson's ratio. So the correction factor would come out to be my actual SG. So what is the strain here? If I see epsilon A is nothing but delta R by R divided by this entire thing, SA into 1 plus KT epsilon T by epsilon A, and my apparent strain, if I see, if I take this to be epsilon A and I equate it, my apparent gauge factor will be Sg divided by Sg into this thing, 1 plus KT epsilon T by epsilon A divided by 1 minus mu epsilon mu KT, I'm sorry. So this is what I will, yes. No, apparent strain is what, okay, apparent strain has the direct formula, but the question is asking for apparent gauge factor. Yeah, Sg hat essentially. which yeah, so that SG hat essentially accounts for the mismatch of the Poisson's ratio between the calibration done, the material on which calibration was done versus the base material on which you are applying it. Okay, so what does this come out to be? Let us calculate this. SG, the gauge factor for this strain gauge is given to be 2 into 1 plus KT was given to be how much? In the question, it was given some percentage, no? Yeah, 1.1%. So essentially, it is 1.1 by 100 into epsilon T by epsilon A. For our problem, epsilon T by epsilon A is, we know that our strain gauge was pasted in the circumferential direction. So epsilon T becomes epsilon L. So that is why we actually calculated that ratio of epsilon L by epsilon H. Okay, this is nothing but our epsilon L by epsilon H. Because our strain gauge is pasted in the circumferential direction for which axial strain is epsilon H. So I hope that is clear. Into what was that ratio that we calculated here somewhere? 0.246, exactly. 0.246 divided by 1 minus mu. Now mu we are supposed to, yeah, no, mu we are supposed to account for this, yeah, 0.285, because that is what the calibration beam was. That is what the gauge Poisson's ratio of the calibration beam was, based on which they have come up with this. Generally, that is what is used, but it is given in the question. In case of actual application of strain gauges, the pamphlet that will be provided by the strain gauge manufacturer will mention this. Okay. Yeah. One. Yeah. One. Yes. Yeah. Okay. I hope that is clear. Into KT. So what does this come out to be? 2 into, so 2.012 is SG hat. So we are able to see we were given a strain gauge of gauge factor 2, but actual apparent gauge factor after this correction is 2.012. So if we take this and multiply it with our strain gauge reading, which is essentially the apparent strain, then we will be getting strain measurements that are accounted for this mismatch of Poisson's effect. Okay, now this is 2.012. All right. What is the percentage error introduced if the transfer sensitivity is not taken into account? This, what do you mean? 100? Yeah. Percentage error. You can revisit the lecture for this once. It's a little lengthy derivation, so I'm not deriving it as of now, but I'll just straight away write the result. Et by Ea for the application divided by 1 minus mu naught Kt into 100, of course. So this will be 0.11 into 0. Uh, I I couldn't answer to that. In general, the theory will be covered. So if at all these come, I don't think it is that complex to once you get how strain gauges work, this is a matter of deriving in 2 minutes. So no, that is what I'm saying, that some things are very simple to derive. Now, for example, if we go to photoelastic coatings, there we have correction factors that are one half a page long. So naturally, people will not be expected to remember all that. So in such cases, mostly these things will be given. But some understanding of the fundamentals needs to be there. So in such cases, I think once you just go through the derivations for strain gauge, I don't think there is anything complex about it. I'm sure you'll be able to find this easily. No, no, of course, they will not be asking values from graphs and all that. See, whatever is relevant for you, even you see, this is the sample, like a sample question, you can say. So, whatever are the essential components of the question, those are already given. Over and above this, considering time, if they feel that there is something which is quite lengthy for derivation, naturally they will make provisions for it. Okay. Yeah. Yeah. All right. So, where were we? We were here, no? Yeah. Yeah. So, this is 0.285 plus our ratio that came to 0.245, I suppose. 0.246 by 1 minus 0.285. May not put any not there. Just me. Yeah. Mu is given here, no? Into 100, of course, for percentage. So this is 0.59% error. This is my error if I don't consider transverse sensitivity effect. Whether this is appreciable or not, that will depend on how sensitive a measurement we are trying to take. All right. Okay. So let us look at this question. The strain field in a component of interest. There is some component which we are trying to study, and the strain field there in the range x ranging between minus 5 and 5 is given by this polynomial. So it is following this form. So if you were to plot this polynomial in the range minus 5 to 5, you will be able to see what the strain field is like. Okay. When x is substituted in millimeters, the expression gives strain in microstrain, where x belongs to minus 5 mm to 5 mm at the point of interest. A general purpose strain gauge of gauge length 2 mm, 2 mm gauge length, gauge. is what is available for measurement. So this is a constraint from site. This is what we have. If the strain gauge is pasted such that its center, the strain gauge is 2 mm long, 2 mm long, and its center lies at x equal to minus 3, minus 3 mm. Yeah. So if I were to draw this point is minus 3, this will be minus 4, this will be minus 5, minus 2, minus 1, and let this be 0. So this is how it has been pasted. Answer the following question based on the given data is what we are asked. So between minus 4 and minus 2 also there is strain variation, and that strain varies according to this polynomial. But we have pasted a strain gauge with the strain gauge center at minus 3. So what are the differences that will arise from this is what we are trying to see. So what is the average strain? If it was a linear variation, we could have simply taken the values here and averaged them out. But as we can see, it is a nonlinear variation. Essentially, it's a cubic variation. In such cases, our strain between minus 4 and minus 2, this is minus 2, minus 4, will have some sort of a variation. So what is the average of this? How we will calculate the average? We have to integrate this over the limit and normalize it by the width. This is minus 4. So this width is 2 mm. Absolute distance is 2 mm. So that area divided by 2 mm will give me the average. What is average? Essentially, we are trying to model this same strain using some average strain, epsilon average, such that epsilon average into this 2 mm gives me the same sum total of the strain in that area. So that is how we'll calculate this. Okay, so strain variation, strain is given by, or rather let me write it this way, strain as a function of x is given by 5x cube plus 3x square plus 4x plus 3x squared plus 4x. So average is nothing but my integration. My limits will be minus 2 to minus 4 into 5x cube plus 3x squared plus 4x dx divided by b minus 6, minus 4 minus 2. Okay, so what does this come out to be? I'll just do it with a calculator to save some time. Yeah, difference of the limits, no? Yes, yes. Plus 3x squared plus 4x. So this is 268 divided by minus 2, which is minus 134 microstrain is the average strain. Okay, so this is the average strain. It is pasted between these 2 points, no? This is -4, this is -2, this is the x-axis. You read the question, no? If the strain gauge is pasted such that its center is at -3, the strain gauge length is 2 mm. Strain gauge length is 2 mm. Its center is at -3. So what will left and right side be? -2 and -4, right? Yeah. Yeah. The actual strain EP at the point will be what? It is nothing but when I substitute x equal to -3. So what will that come out to be? 5 into -3 cube plus 3 into -3 squared plus 4 into -3. This is the point strain plus 4 into -3. So it is 3 into -3 squared. Yeah, was there some? Okay. Yeah, how much are you getting? Okay, so as of now, I'll just put what I'm getting. Minus 459 microstrain. So you can just check this value if this is what you're getting. Okay. The absolute error made in the measurement of epsilon xx is error. Absolute error is at that point minus epsilon average by epsilon at that point into 100. What does this come out to be? 137, right? 134. So minus 134, 459 by, so it is nearly twice 200%. Something is off, but anyway, in the interest of carrying this forward, I'll just go with this for now. Okay, so this is minus 242%. That is almost twice. No, we are able to see 134 is the actual average strain is what we're getting, but at that point it is 459 microstrain. Okay, that is because this variation is so sharp at that point. If we see the graph, it will have some peak over there. That is what is pulling up the thing. Lest there is no mathematical error. Okay, the absolute error in microstrain in measurement of epsilon xs if the strain gauge is pasted such that its center is at x equal to 0 is what is asked. Okay, so if the strain gauge is pasted at x equal to 0. Let me do it here. It's the same scenario. My strain gauge is like that, and I have my this thing. This is 1, 0, -1, and so on. This is -2, and this is 2. So the error, the question asks, what is the absolute error in the measurement of epsilon xx if the strain gauge is pasted such that its center is at center is at x equal to 0. Now we can see from our strain field that at x equal to 0, strain goes to 0. So let me call this the center. So epsilon c is 0 from my distribution given. Now from strain gauge, what will this come out to be? -1 to 1, 5x cube plus 3x squared plus 4x dx by 1 minus 1. So what does this come out to be? -1 to 1, 5x cube plus 3 squared plus 4x -1 to 1. It is 2 by 2. This is 1 microstrain. Okay. So the absolute error in microstrain is this epsilon c minus epsilon c average. This is nothing but 1 microstrain. Okay. The absolute error made in the measurement of epsilon xx as a percentage of the actual strain epsilon p if the strain gauge is pasted such that its center is at 2. It is the same drill. We don't need to do it time and again, but for the sake of this thing, let us complete it. Case 3. Now P or the center is at X that we need to consider is at 2 mm. So epsilon at the point of interest is 5 into 2 cube plus 3 into 2 squared plus 4 into 2. 8 5s are 40 plus 3 4s are 12. 40, 52, 60. This is 60 microstrain from our distribution. What will our strain gauge see? Let me just copy the same thing and put it here. Now these numbers will change. Okay, I have this at 2. So this will be 1, this is 3, 4, and so on. This will be 0. And this is not C, this is P. Okay, so the average strain that is getting measured is integration 1 to 3, 5x cubed plus 3x squared plus 4x dx by 2. So let us calculate this. 5x cubed plus 3x squared plus 4x. So this comes to 142 microstrain by 2, which is 71 microstrain. All right. So the error in terms of percentage, absolute error in terms of percentage of the absolute strain EP, of the actual strain EP is asked. So error percentage will be EP minus average by epsilon p into 100, which is 70. The actual strain was 60 minus 71 by 60 to 100, which comes out to be 11 by 60 into 100 is 18.3%, which makes sense. It's close by. So only for this case, only for the first case where this was placed somewhere on the left side, there seems to be some discrepancy somewhere. I'll check this. You guys can also have a look. When I'll post this, I'll check this and post it if it is so. Okay. So I hope that that is clear. So other than that, I have run out of questions. So if there are any questions, I welcome them. Where? Which one? Yeah, the absolute error is what we are reporting, no? Oh, yeah. Yeah. The absolute error made in the measurement of epsilon xx has a percentage of actual strain epsilon p. If the strain gauge is pasted such that its center is at x equal to 2 mm. Anyway, whatever be that 200% or whatever be the variation, I hope that you have got the gist of the problem. Essentially, what does this problem try to convey? That we are trying to measure strain at a point. Yeah, just a moment, we'll come to that. We are trying to measure strain at a point, but our strain gauge has finite length. So it is essentially measuring only average strain. Now, hypothetically, we have been given some distribution in this case, and we have been asked to quantify the strain. So as to make ourselves sensitive that strain at a point is different from average strain. And it could shoot up depending on your high gradient zone. Let us say if this was a high gradient zone, meaning strains climb up very steeply with X variation. In such cases, we should go for smaller gauge lengths. That is the message this question is trying to convey, irrespective of whether it's 242 and 459 and all that. I hope you have understood the gist of the problem. It is the entire essence of this initiative. So I hope that that is conveyed. Train at different. Yeah. Yes. Yeah. They have given the range and they are trying to ask strains at different points as opposed to what our strain gauge will report. Our strain gauge will report something else, right? Because it is averaging over its gauge length. So when our gradient of the strain is not steep, meaning the slope of this curve, the slope of this curve, when it is not steep, the difference won't be much. If it is very steep, then the difference will be high. Okay. So I hope that that is clear. Yes, someone had one question. I have a doubt in question 8, 9, and 10 of week 8 assignment. Okay. So have you seen the PDF that I have posted that has the solution? What is the question, sir? Mr. Pranav Gedam, Gedam, where you had posted it? These PDF, this session PDFs, I'm uploading it to one drive. No, it is available on the Swayam portal. Mr. Rajamana, are you aware of that? Yeah, yeah. YouTube videos I'm uploading. If you go to the Swayam portal page, on the bottom left, it will say live sessions. Yes, yes. Yeah. So in that problem solving session, if you see, it will take you to a drive where I have posted the solutions to these previous year. Your question is from the current year assignment or the one that I had solved? That is important to know. That I am not sure. That you will have to check with the website because I am not very abreast with that change. Oh, it is from the current year, is it? Okay, current year I am not solving. Okay, but you, why don't you ask what is the question? Because I don't have the question up with me right away. I'll try to get it. In the meantime, if you have it, why don't you ask what it was? I'll try to provide some. Yes. Huh. No, that formula list actually even professor recommends the students to make it so that at least that way they will learn what is important and what is not. Because the yes, because the course is so elaborate, because the course is so elaborate that students are actually they have to gauge which is important, more important based on the assignments that were asked, which is more important, and they have to make that list. So in such a case, you can make it, and why don't, if you make it, you can even send it to our forum. The students, the TAs there will try to answer that. Okay, yeah. Some regions of the fiber, yeah, okay. Huh. Yeah, that is because in the case, oh, 1 minute, sir, Mr. Pranav, I'll come to your question 1 minute. No, that is because in case of multiple select, if one ticks all the answers, it is to discourage guessing. That is why it is done. It is a NPTEL's policy. This is not done by the TAs. Yeah, that partially correct will happen. Let us say if a question has three correct answers, if you select only two out of those three correct answers, you will be given partial marks. If you select all the three correct, yes. If you select, yeah, if you select even one wrong answer, it will lead to total loss of the marks. That is to discourage guessing, because in a multiple select, anyone can select all the options and be done with it. If they are not if that is not penalized, then the score will go to them also. Whoever is giving just simply ticking all the answers should not give them marks, right? Yeah, NPTEL's policy. Okay. Some regions of a fiber reinforced plastic board needs to be studied using photoelastic coating. Okay. A coating suitable for the study of non-metallic is selected and the calibration, this thing is given, is sought by applying a tension test to the coating directly by transmission photoelasticity. It is proposed to use white light. Okay. The test section. Ah, what is the issue here? Similar question we have solved in week 8 also, no? See, essentially what they are trying to do is now we have a specimen over which we want to apply a photoelastic coating. This coating we want to apply. For that, we need to calibrate that photoelastic coating. Yeah, strain coefficient K is nothing but our F, no, sorry, F epsilon is nothing but K by, sorry, lambda by K, or lambda is, sorry, K is by F epsilon. Now you have another relation between F epsilon and F sigma. For a case of uniaxial tension, okay, that's fine. I'll just briefly explain it to you. For a case of uniaxial tension, You have a specimen, you pull it with sigma, sigma. So in this case, sigma 1 equal to sigma 2 equal to 0. So sigma 1 minus sigma 2 is nothing but our sigma. It is n f sigma by t, right? So the fringe order observed is 2.6. So n is given. Whatever stress was applied is given, n is given, t is given. So from here you calculate f sigma. Now from f sigma you find out what is the relationship between f sigma and f epsilon. It is some ratio of e function of e and mu. Okay, those things also will be given. Based on that, you calculate f epsilon. You have been given lambda. By that, you can calculate your strain optic coefficient. So I would suggest you give it a try. Also, Mr. Pranav, what you can do is on the Swayam portal homepage on the left side, I hope that you are aware that live sessions are being uploaded. There, I have uploaded the video solving similar questions from week 8. So that live session video you can refer if you want. Otherwise, there are also PDFs where, for example, today I have solved these questions. No, similar to that, I would have solved for week 8 and I would have uploaded that PDF. So you can just take a look at that. That club with these tips that I have given, it should be enough for you to solve that, approach that problem. So I would recommend that you try it once with this background of understanding. And if you still have any questions, you can post it in the forum and we will answer that. In the discussion forum, you can post that and we'll answer. Okay, yeah, all right. Yes, yeah, yeah, okay, yeah, yeah, yeah. Yes, have you seen the lectures? It is given in the lecture. There is one root over 8 by 3, something like that will come. No, then it must be because of the conversion factor, perhaps. Have you converted all to the same unit? Uh, in that case, you check your units once because see wherever, yeah, yeah, you just, yeah, that's fine. You just ensure one thing that the unit conversion is correct because we are dealing with a square root here. Whenever we deal with a square root, 10 and 10 power 3, they give very, very different results. Okay, so you check your units once. If you are still convinced that you, ah, yeah, okay. Yeah, you just substitute and see once. What I'm saying is, I would suggest that because a root is involved, it can become tricky at times. So what I would suggest is you just calculate it once again with that formula is there, no? E into root over 8 by 3 pi r something. Based on that, you calculate, substitute it, and if you are still convinced that what you have done is correct, then you please post it in the forum. Yes, naturally, one microstrain is 10 power minus 6, right? 10 power minus 6. Yes, mm per mm. This is what it implies. Yeah. If you are still not getting the correct answer, then if you are convinced that you have done the things correctly, then you should raise it in the forum. Okay, the TAs will attend to this immediately. All right. 6, yes. Right. Yeah, that's what I'm saying. So if you are convinced that what you've done is correct, then you should raise it in the forum. Okay. Yeah. Yeah. How much is the K1 they are giving? Okay. I see. Okay. No, no, but mode 1 in which unit they are asking? See, K1 has a very funny unit, okay? It is MPa root meter. They are asking in MPa root meter, is it? Okay. What have you done? 70 GPa they have given. Yeah, into 10 power 3, that's fine. 70 E3 into root of uh, 2 mm into 10 power minus 3 meter, na? Because they have asked it in root meter, no? Yeah, but here it is asked in root meter, na? Right? Yeah, so you need to pay attention to the units. Yeah, yeah, right. That's fine, that's fine. You needn't get diffident over it. You have given it an attempt. At least this way you will remember that units play a vital role. That is what I was saying. Because if it is that if this root over is not there, it is simple 1,000th of it. But since that root over is there, it is not the same thing. It will come to some a factor of 32 or something like that. That is why it matters. Yeah, yeah. Right, right. That's fine. That's all right. Don't get disappointed. It's okay. It's a learning curve. So at least in the exam, you can pay attention to this. Okay. Yeah. Yeah. Okay. Okay. So with this, actually, we come to the close of these sessions. So we have right from photoelasticity, transmission photoelasticity, reflection photoelasticity, then RGB, basics of three-dimensional photoelasticity. Then we saw some brittle coating methods as such, which had to do with photoelastic coating, brittle coatings. Then we came to our this thing, strain gauges. Then strain gauge in detail, we have seen almost about 2 to 3 weeks, I think, has been spent on strain gauges. So all the recorded sessions, I have I have make it a point that I post it immediately. So this to almost by tonight it will be available on that link that they have given on the Swayam portal, as well as this PDF where I'm solving these questions. If I have not written something legibly, I try to neatly write it and I post this also. So this also can be found in the same drive folder that is given in the Swayam portal homepage. So with this, we have covered the entire course, live sessions for 12 weeks. And I have tried to do justice to the initiative by solving it as correctly as possible. If you guys have any other questions, you can ask now. Otherwise, you please feel free to post it in the forum. We'll try to address it as soon as possible. So with that, I don't have anything much to add after this. So I hope that this initiative it served some purpose for you and it helped you out in some way. If it did, I would consider this initiative a success. So thank you. If you have any questions, please feel free to ask. Otherwise, I'd like to call it a day. So all the best for those who are taking the exam. And perhaps we'll meet in the coming semesters. Yeah, yes, yeah, mostly, yes, exactly. So, for in order to prepare for the final exam, you try to go through the lectures, your notes that you have taken, and try to attempt the assignment problems. And whatever doubts you have, you get it clarified by the forum. Or you can also watch the live session series that we did. Perhaps that could help you out in some way. Okay, nothing. that, no, see, essentially, what can be done other than this? Sky is the limit, right? Right. So, exactly. Yeah, I understand your point. So, given the time constraint, I would say that this would be a nice refresher. If you could go through the assignment questions and thoroughly understand the concepts that were asked, I suppose that should suffice as a good enough refresher. How to calculate? Yeah, you can contact through the forum. No, you can ask any question there. Not a problem. Okay. Yeah. Okay. All right. Thank you. Thank you very much. So, in case there are no further questions, I'd like to call it a day. Thank you for attending these sessions. Uh, so, we'll see you around perhaps in the next semester or so. So, all the best. Thanks. So, I'll end the call with this. Thanks.